Today I'm going to talk about control replication, a technique for compiling implicitly parallel programs to execute efficiently on large supercomputers. Implicit parallelism is nothing new. The idea goes back to the original work on auto-parallelizing compilers in the late 80s and 90s. And the idea is to take a program like this one. This is just a simple 5-point stencil on a 2D array. And to take a code like this one and to automatically compile it to execute efficiently on a parallel machine. And that means identifying the memory access patterns in these inner loops, determining what's able to execute in parallel, and subdividing the problem so that it can execute. And this is something that we can do reasonably well in a static compiler. But the applicability of these approaches is rather limited. We can apply these approaches to structured codes like these ones with relatively simple indexing patterns on the arrays. But there are codes that are very similar to these, but add a little bit more dynamic behavior that can't be addressed with these approaches. So for example, here's a code that's very similar to the first code. All we've really done is we've changed a little bit about the index math that we're doing to access these arrays. And because this expression could potentially be dynamic, this is not something that we can analyze in a compiler. And so, for example, this is a pattern that shows up quite commonly. This might be, say, an unstructured mesh. And this requires a different kind of technique. The most well-known technique is the inspector-executor method, which has been also very well investigated. First appeared again in the late 80s and has been recently re-explored in some very nice work that appeared in PPOP in 2012. This approach, the basic idea is to do a dynamic analysis of the individual memory access patterns in the application. Using that dynamic analysis, along with some sort of graph partitioning, we can automatically convert these programs to execute on a parallel computer. The problem is that the dynamic analysis of these access patterns can be potentially expensive, both in the time cost and in the memory cost of that analysis. In the worst case, it might not be possible to execute an application at all if the problem size that you're executing is too large or the scale of the machine is too large. And so on the one hand, we've got an approach which works well but has very limited applicability, and on the other hand, we've got a technique which is very general but is potentially too expensive to use. Recently, there has been another class of work that has been gaining momentum called task-based implicitly parallel programs. The basic idea of this approach is to take the inner loops from before and turn those into tasks, which you can think of as just being functions, and then after we do this, we phrase the main program in terms of these tasks instead of writing out the inner loops like we did before. And notice the advantage of doing this is that these tasks, the programs based on these tasks, reference bulk units of data instead of the individual elements, and so we can perform this analysis now at a coarser granularity, which makes the dynamic analysis feasible. We can now do a dynamic analysis without paying quite so steep a cost for that analysis. This can work very well, but it can still potentially be expensive, and in particular, the analysis of these tasks can become a sequential bottleneck. And so in this work, what we focus on is automatically generating efficient SPIMD code from these task-based programs. In particular, our goal is to make these programs scale to large supercomputers. And the way that we're going to do that is by achieving an asymptotic reduction in the steady state cost of this dynamic analysis. In particular, we're going to reduce it to a constant factor rather than a linear factor in the number of nodes. So, let's just quickly walk through how we're going to do this. First, I'm going to walk through what an execution of a task-based program would look like without the control replication optimization. So I'm going to assume that these task-based models provide sequential semantics. That is, you can view the tasks as forming a stream in the program order that they're originally executed in. So we've got this stream of tasks, and the system is responsible for finding parallelism between those tasks by analyzing dependencies between the arguments to those tasks. You can think of this dependency analysis as producing what is effectively a data flow graph, which determines the constraints that must be obeyed when executing the program. This data flow graph captures essentially the parallelism that exists in the application. That data flow graph is then scheduled, and in particular, when we divide the tasks between different nodes in a distributed memory machine, any place where an edge crosses from one node to another in this data flow graph, we have to insert a copy operation to move the data from one node to the other. So the system is responsible for discovering parallelism, and the system is also responsible for all data movement that occurs in the program. Now there's something that I want to point out about this structure, and that is that the analysis of these tasks is sequential. Because the tasks come in a stream, and because we don't inherently know anything about the structure of these tasks, we have to do a sequential analysis of one task at a time in order to determine where the parallelism is in the application. And at some scale, that's going to become a bottleneck no matter how fast that analysis is. And so what we're going to do in a control replicated execution is we're going to use the compiler to split this single stream of tasks into multiple streams that are going to be able to execute in parallel. So we just take the tasks, we split them up between these multiple streams of execution, and each stream of execution proceeds as if it's completely independent from every other stream. So we compute the data flow graph using this dependence analysis independently for each stream. We schedule the execution, again, independently for each stream, and then we arrive at an execution of this program. But you might notice that there's something wrong about the execution that we've got on the bottom of this diagram. That is, the copy that we had determined was necessary in order to execute the program correctly in the original execution is missing in the control replicated execution. And so in order to make the program be correct, any place where a copy was required to be inserted in the original execution, the compiler, in performing control replication, is going to need to insert that copy on its own and also insert synchronization to make sure that the copy is properly synchronized with any task in any other stream that is going to depend on that copy. The rest of the dependence analysis is going to flow through as it did before, and in this way we achieve a correct execution of the program. So there are two things that I want to point out about this execution with the control replication optimization. One is that the control replication optimization is effectively transforming the program from this sequential semantics that existed originally into what is effectively a SC17 semantics, because each stream is processed independently and each stream is oblivious to any operations that occur in any other stream. You can see this as being similar to a SC17 semantics of a program. And because of that transformation, because we're now operating the different streams in parallel, that means that the dynamic analysis component of the system is now going to be able to execute in parallel. And if we assume that the number of tasks to be executed is proportional to the number of nodes, then as we scale out, we're going to keep a constant amount of analysis work per node. So let's just briefly go over the steps in the transformation. I'm not going to have time to go through every step in full in this paper, but we're going to select a number of steps to discuss in more detail. So first, at compile time, the transformation takes these loops of tasks in the original program and splits those tasks between streams. The compiler inserts copies in any place where there is a dependence that crosses from one stream to another, and inserts synchronization with the task that that got cut off on the other side. At runtime, there are various things that we need to do to make sure that the execution of the program is efficient. We need to determine the precise communication graph. This is something that is potentially a dynamic property of the program, and so we can't do it precisely at compile time. And we need to determine the precise amount of data that needs to be copied so that we're not copying too much data. The rest of the pipeline at runtime is the same. We perform dependence analysis and we perform scheduling as we did before. So again, see the paper for the full details on these steps. In this talk, we're going to focus on the copies and the dynamic analysis to determine exactly what data needs to be moved at runtime. So before I describe this, I need to describe a little bit more about the programming model. So in this model, a task is a unit of computation. You can think of it as being a function to be executed in parallel. So for example, a task is going to take arguments, and a task is going to name privileges on those arguments that specify whether it reads or writes the data in each respective argument. So in this case, this task TG is going to read and write the data in the own argument, and it's going to read the data in the halo argument. And then the body of the task is just going to look like some piece of sequential code. This could be something coming from an advection in a Lagrangian simulation on an unstructured mesh, for example. But this is just some piece of sequential code that you write over the data structures, the arguments to the task. The task itself is going to operate on regions, which are units of data. You can think of them as being similar to arrays, but they're more flexible. They move around the machine to where the tasks are being executed, and so they're not fixed in a single location in memory like you would expect from a traditional array. So typically in these programs, there will be a main task, and that main task will declare some number of regions that represent the data structures in the program. So in this case, we're going to create a mesh of cells, and then in order to operate on the pieces of the mesh in parallel, we're going to explicitly partition it into subregions. So a partition is a first-class data type in this model, and a partition essentially divides a region into some set of subpieces that we can then execute tasks on. And the advantage of doing this is that the user can specify exactly what pieces of the data structure they want to execute on. And we're going to continue doing this. The user can declare multiple partitions in order to select the pieces of the mesh that are relevant for various purposes. So in this case, we're declaring the pieces of the mesh that are owned by each piece of the computation, and then the halos around those pieces that are going to be used in data exchanges. And in general, the user can do this an arbitrary number of times to identify any arbitrary subsets of the data that are of interest to the program. And then finally, the execution of the program just follows sequential semantics. So typically, if you have, for example, a time step loop, you just write out the code to call those tasks in the order that they should be executed in. And the user doesn't have to think about the parallelism or the data movement in the program. This is a complete description of the program. And so what we're going to focus on in the rest of the talk is the copies that need to be inserted by the compiler in order to make the control replication optimization correct. Now, a copy occurs whenever there are two tasks that execute in different streams, and the arguments to those tasks overlap, and at least one task writes. Now, the task privileges, read or write, are statically known, and so that's trivial for the compiler to determine. The critical questions are which pairs of argument regions can possibly overlap, and which exact elements of those regions are going to need to be copied from one node to another. Now, these are not questions that you can fully answer in a static compiler analysis. We're going to need to use some form of dynamic analysis. But in this case, we're going to use a hybrid analysis that is going to limit the amount of runtime cost and therefore allow the system to scale. So for example, If we have two tasks, task A writes some subset of this, some subregion of this mesh, and then task B reads from an overlapping subregion. Then the overlap between those two regions is going to be the set of data that we need to communicate if those two tasks execute on different nodes. And so the real question here is about the data, and this question really comes down to the partitioning in the application. And so next I have to describe a couple of things about how partitioning works in order to show you how this analysis is going to proceed in the compiler. Now, partitions can be quite expressive. They can name arbitrary subsets of the elements. And partitions can be either disjoint or aliased. A disjoint partition means that the subregions that are being named in the partition operation are non-overlapping. And that means that we're going to be able to execute them on them in parallel. But it is also useful to be able to name non-overlapping subsets of data. So for example, this was the case where we had an overlapping read, and basically this ability to declare an aliased or an overlapping partition gave us more expressive power to describe what the program was doing. So this is one of the things that you can do with partitions. You can also declare multiple partitions of the same region. So for example, you could partition a region by rows, and you could also partition a region by columns, and the system will automatically manage the copies between these if you have, say, an application that has phases and it flips back and forth between these two access patterns. And finally, partitions can be nested. So for example, you could have a grid that you partition by into one piece per node, and then you could take each of those pieces and partition it into one piece per core. And this would give you, again, an ability to describe in great detail what exactly you want your computation to be doing. Now, it's worth noting that these nested partitions can be viewed as a tree. So where you basically have one node in the tree for each region or partition operation that you perform. So in this case, we'd have a node for the overall grid. We have a node that corresponds to the partition itself that subdivides this grid into pieces. That gives us one piece for or each of the nodes, and then we have a subtree for each of those nodes that divides that the subgrid for the node into a piece per core. And the analysis that we're going to be doing in the compiler is going to take advantage of this view in order to perform certain kinds of static analysis on the shape of these trees at compile time. So in particular, what we're going to do is we have what we call a region tree algorithm that statically checks for possible overlaps between two regions using this tree structure that I described earlier. This is a conservative analysis, but it's good enough. And in particular, what it does is it allows us to reduce the cost of any subsequent dynamic analysis by skipping basically this overlap analysis for any regions that we can statically know to be non-overlapping. Basically, how the algorithm works is that for any two nodes in the tree, we walk up the tree to the least common ancestor, and if that ancestor is a disjoint partition, then we know that the two subregions are also disjoint. If that ancestor is anything else, for example, an alias partition or a region, then we know that those two nodes could potentially overlap. And again, this analysis allows us to reduce the amount of dynamic analysis that we'll do in subsequent stages. So this analysis helps us determine the static locations in the program where we need to insert copies. Based on the privileges and the potential for overlap, we know that we need to insert copies into the program in certain places. But in order for those copies to be efficient, we need to make sure that we only issue copies when the actual runtime, the actual contents of these regions at runtime contains the overlap that we determined could potentially happen at compile time. And so in order to do that, we perform some runtime dynamic analysis in order to determine which pairs of regions actually overlap during the execution of the program. And we do this dynamic analysis in two phases. First, we determine which pairs of regions could potentially overlap, but we explicitly ignore the exact extent of that overlap. This essentially allows us to determine the communication graph of the program at runtime. And because we're not attempting to determine the exact extent of the overlap between these regions, we can optimize this analysis using a bounding volume hierarchy in order to make it n log n in the number of nodes. We do perform this analysis on one node, but we perform it at startup, and so the overall cost of this analysis is quite small compared to the execution time of the program. But it's also important to make sure that when we issue copies, we're only copying exactly the data that we need to copy, because the communication on these distributed machines is so expensive compared to compute. And so we follow this with a second dynamic analysis that determines exactly which elements are contained in that overlap. And we perform this analysis in approximately O of m squared time, where m is the degree of the communication graph at any given node in the machine. So if the machine is performing, for example, a stencil operation where it's doing a halo exchange with its neighbors, this is going to be a constant factor in the number of nodes, and so this cost is going to stay low overall. And again, we perform this analysis on every node in the machine in parallel. And it's also performed at startup like the other analysis. So in order to evaluate the viability of this approach, we implemented a prototype of control replication in the Regent programming language and performed some experiments on the Pisdane supercomputer. And the goal of these experiments is to show an asymptotic reduction in the steady state cost of this dynamic analysis. And in particular, what should happen is if we're doing weak scaling, when we get out to a sufficiently large number of nodes, what we should be able to see is that if the analysis cost stays a constant factor in the number of nodes, we should get very good weak scaling. And so that's what we're aiming to show with these experiments. So we performed this experiments on a number of applications. This is the stencil application from the parallel research kernels. Again, this is a weak scaling plot, and so a perfectly flat line would be optimal performance in this graph. And what we can see is that control replication, which is the red line here, gets very close to the MPI performance. We're at 99% parallel efficiency, and we're within essentially about 1% of absolute performance of the MPI code. And in comparison, without control replication, the performance initially stays good, but after a certain point, the performance drops rapidly. And the thing that's going on here is that the dynamic analysis that needs to be performed is initially performed in parallel with the application, and so it's completely hidden as long as it's small enough. But because it grows asymptotically, at some point it's going to exceed the overall execution time of the program, and after that point the performance drops very rapidly. And this is basically the pattern that we see with all of our applications. With control, again, the red line in each of these plots is control replication, and in each case we get very good weak scalability with that optimization enabled. And if we turn the optimization off, then the program scales up to a point but then drops off after that. And then finally, we also evaluated a hybrid application. This is Soleil X, which uses a combination of a fluid simulation on a structured mesh with particle simulation. And again, we were able to scale this out to 1,000 nodes. And finally, I wanted to say something about the cost of the dynamic analysis, because that is potentially a concern. For all of the applications we tested at 1,000 nodes, the cost of this analysis was at most 260 milliseconds. Again, this is incurred once at the startup time of the application, And so for long-running applications, this is not a significant factor. We'd like to acknowledge funding from a number of sources, including the Army High Performance Computing Research Center, the Department of Energy, and the Swiss National Supercomputing Center. And with that, I'd be happy to take any questions. Thank you.